Okay, and come back to the share. Okay, here we go. So what I'm going to present here is just the basic idea of the derivative. This is the main thing that we study in this course. So this is the section called Preview of Calculus. I might say the calculus. Sometimes people say the calculus when they're feeling kind of pretentious. So preview of calculus. And in particular, we're going to look at the derivative. So the idea of the derivative came out of a physics question about velocity. So let's say that we have something that moves. Like I said in the last class, we can only handle one-dimensional motion here. So it has to be something that moves in a straight line. That just makes the math simpler. When you get later, if you go on to take other math classes, more advanced calculus classes, then you'll learn how to deal with more variables. But we're just going to deal with one variable. Let's say there's a little boat. It could be a train or whatever. And it's going to move from 0 feet over to 10 feet. All right. So we'll say that it started at rest, and then it doesn't want to crash into the dock maybe, so it also slows down before it arrives. So if you think about with a graph, it's terrible. The graph of distance versus time. Okay. So let's say this axis is time and this axis is distance. So in calculus, the letter D, you use it a lot for derivatives, so it's kind of taken. So for distance, we use S. I'm not really sure why, but we do. So I'm going to use the letter T to talk about, S to talk about distance, and T to talk about time. And if you think about what this graph might look like, so the boat initially starts out going kind of slowly. So it's kind of doesn't move far from the dock at first, and then it gets up kind of ahead of steam here, somewhere around there. And then it starts to slow down so that it doesn't smash into the other dock. It might look something kind of like this, right? So here, let's say that it arrives at time t equals 10 seconds. So the entire trip took 10 seconds from 0 all the way over to 10. All right, and let's pick a point to focus on. Let's focus on 2. You could pick some other point here if you wanted to. So we have distance, and you might ask this question. So physicists in the 1600s would ask this question. First, somebody had to come up with the idea of like a graphical representation of an equation and things like that. But once they had the algebra to ask this question, you could say, how fast is the boat moving at time t equals 2? So it seems like we have enough information here to determine the answer to this question. It turns out we do. So you can imagine what we want to do is sort of look at the speedometer of the boat, if it had one. So one thing you might look at when asking this question is, how did they do it in actual boats? And I happen to know that we have one student here from the Coast Guard. And I think Lewis, right? Lewis, can you tell us how they actually determine how fast a boat is going at a given time? You might be muted. You don't have to speak up if you don't want to. So while you're thinking, I'm going to come over here and show you a picture. So you can Google nautical knot common log, and if you look at it might be here, this right? I want a picture. Yeah. So what you have here is like some triangular thing that's designed to drag in the water, and then you have a spool of rope. And in the rope at regular intervals, there are knots. You can see one right there. So what they do is they have this hourglass here, and they throw this thing in the water, and then as the ship moves, this thing freely unspools. And they count how many knots go by until the sand in the hourglass has completely gone down to the bottom. And so that is how many knots the boat is going. So roughly the idea there, if we come back here, is they look at a little bit of distance. So the distance that they go is how far the rope gets unspooled, and then the time that's elapsed is however long the hourglass lasts. So what they're saying here is that the velocity at t equals 2 is approximately, I'll write this as v2. So this is, I'm going to write it as approximately equal to. So you take a little change in distance, and remember we're using s to stand for distance, and you divide that by a little change in time, and what you actually get here, so the reason I wrote that it's approximately equal instead of exactly equal, is because this is actually the average velocity over a short time interval. And if you're asking this question about time t equals 2, which we are, you can actually say which time interval that is. That would be the time interval from 2 to 2 plus delta t. So I don't know how, maybe that hourglass was like a minute timer or 30 seconds or something. That might just be like, our boat is working on different scales here than actual boats. So the units don't quite work if we make delta t be a minute. But so you get the average velocity over a short time interval. So let's actually play around with this. So I've come up with a function that describes a shape that's basically like this. Years from now, if you go on to take a machine learning class, this will actually come up again. It's kind of a famous function called the logistic function. So f of t equals 10 over 1 plus e to the 5 minus t. Okay. And all right, I have, I'm going to look at a plot of this function just to show you the similarity. I actually have a bunch of links for you. And this is the first one. So I'm going to come back to the chat window. I have to stop sharing to get to my chat window. And I see the question in the chat now. So yeah, that question is slightly different from yours, John. Some of them are randomized. The good ones are randomized, so each student sees a different number. So I just in the chat, I just gave everybody a link to the Desmos calculator. And I'm going to come back here, and I'm going to follow this link myself. Right. And so what you see here, I think I might have turned off my projector mode. This red line is the line that I should call it a curve. This red curve is the curve that I kind of crudely sketched. You can see it starts off kind of near 0 here, and then after 10 seconds, it gets all the way up to 10. So it goes 10 feet in 10 seconds, but it doesn't go at a uniform speed. It starts off slow and then speeds up and then slows down again. So on the y-axis here, you have distance in feet, and on the x-axis here, you have distance in seconds. So this purple curve, there's a lot of details here, just ignore those for the time being. This purple curve is like the speedometer. And the height of the purple curve will tell you at a given time how fast the boat is going. If I click here, you can see that what this tells me is that at time 4, the boat is going approximately 2 feet per second. You can actually kind of cheat and get an answer to our question. So at time 2, the boat is going approximately 0.45 feet per second. But you know, we're trying to learn how this stuff works from first principles, so we don't want to just cheat. And by the way, where did this function come from? I just I made it up. Or I produced it according to a secret method, which is sort of what you're learning. So I'm slowly teaching you how to transform this function, which is the distance function, into this function, which is the velocity function. For now, let's just regard that as a magical transformation. But that's the transformation that you're learning how to make in Calculus 2. Okay, so let's come up with an approximation to v of 2, this question that we're trying to answer. And I'm going to give everybody a link over chat. I'm going to come back here to my chat window. And this is a link to, this is just a handy calculator. You can also use it to do Python. So I'm going to go here myself and make it a little bit bigger. All right, and so before I go nuts there, let's just come back here and talk about the plan. So how can I approximate v of 2, all right? So one way I could approximate v of 2 is to look at the average velocity, or I should say this is approximately equal to the average velocity over the time interval, let's just say t equals 2 to t equals 3. So we'll let a whole second go by. So this will be kind of crude.
Professor, can you share your screen, please?
Oh, thank you. Yeah, and please yell at me immediately when I start doing dumb stuff like that. Thank you very much. Okay, so here we are. So v of 2 is going to be approximately equal to the average velocity over the time interval from t equals 2 to t equals 3. All right, so what is this going to be? This is going to be a change in distance over a change in time. Okay, so how are we going to compute that? So we'll use the function notation. You're never going to have to worry about the fact that this thing actually is this complicated function. Or at least for the purposes of this, don't worry about it. So what is the change in location? The change in location is going to be f of 3 minus f of 2. That's how far the boat goes over the time interval from 2 to 3. And the change in time is going to be 3 minus 2, which is just 1. Okay. So according to this plan, we're going to get the average velocity over this time interval, and it's just going to be basically f of 3 minus f of 2. Okay. And you can compute that according to your favorite method. But the method that I'm going to use is to use this Sage cell thing, because I find that it saves a lot of time. So I'm going to do 10 divided by 1 plus the exponential function 5 minus t. Or sorry, I think it has to be x here. I guess I could do t, couldn't I? Should I do t? All right. And let's just do a sanity check here. I think this will just plot the thing. All right. And that actually doesn't look too good. You know what? It's just looking over a really small time scale. It's still the same function. So what it's done there is it's zoomed in right here. So to make these things look the same, we would need to adjust the scale here. But the function is correct. Okay. So we'll call this v2. So this is going to be approximately equal to. I'm just going to now translate into code what I just wrote in text. So this will be f of 3 minus f of 2 divided by 3 minus 2. And so now I'm just going to print out v2. Let's see what comes out. It'll be that. It's kind of annoying the way it does that. So this thing is made for doing calculus, and so it always gives you precisely the right answer with no numerical rounding. But we wanted actually to do numerical rounding because we want an answer we can understand. So I add this. And what I get is 0.71777. All right, so if I come back here to my sheet, what I just got is this approximation for the velocity at time 2. So it's approximately equal to 0.717777, and the units here would be feet per second. All right, great. So this is a rough approximation, because if you look at what's happening over that second from 2 to 3 here, so I go from 2 to 3, the thing is actually kind of accelerating. So here's a way to think of what we just did. We took this, and we took this, and this side of the triangle here is 1, and this side of the triangle is f of 3 minus f of 2, and then we took the ratio of those two things, and so that's kind of rise over run here, and so what we did is we got the slope of this line that connects these two dots. And the problem is that this curve is not a line. If we go back to Desmos, scam likely. If we go back to Desmos, and I'm going to turn on these things now. So let me get my scale right. Okay, so now you can see these two dots. So I've got a slider here. Let me put this one at 3. Okay, and I need to change my scale again. That's right. This has just made the thing disappear. Oops, crap. So I'm just gonna have to manually push this up to 3. All right, there it is, 3. Oh crap, sorry. This Z here actually means something different. So Z should be 1. Okay, there we go. So now I have a point at 2 and a point at 3. And I can look at a line connecting those two. And you can see that the curve is not exactly on that line, because this is this is just not a linear function. So there's a little bit of non-linearity there. And I can draw this triangle with this side. Right, so this side of the triangle, and then this side of the triangle. And then it turns out that this side of the triangle is 1, because it's just 3 minus 2. And this side of the triangle is f of 3 minus f of 2, which turns out to be equal to 0.717777. Okay, we take the ratio of those two, and what it gives us is the slope of this line, which is called the secant line. And the secant depends on this point that you're interested in. So we're interested in this point. And it varies depending on what you choose as the second point here. Okay. So for the second point, we chose 3, but we could have chosen something else. And what we get is the slope of that secant line is 0.7117, or sorry, 0.71777. And now this means two things, right? So on the one hand, this is approximately equal to v of 2, which is the velocity of the ship at time t equals 2. It's approximately equal to that. Geometrically, it's the slope of the secant line. Okay, so here's a question. So this is an approximation. What can we do to make the approximation better?
We could find the area between the red line and the secant line, like the little area in between.
Oh, this little area in between, and that would be a measure of the error. That's
yeah, I'm not sure.
Yeah, that's a good idea. That's a good idea. But let me do this. What if I just make, sorry, I have to turn off drawing. What if I just make this point closer like that? So do you think now that that this is going to be, what we're doing now is we're taking an average, we're taking average velocity, but now it's over a shorter time interval. So do you think that this average velocity over this shorter time interval will be more like the instantaneous velocity of the boat exactly at time 2? Kind of makes sense that it would be, right? And yeah, and it turns out that that idea works. So if you want to improve this, instead of taking the average velocity over t equals 2 to t equals 3, we'll do the same thing, average velocity. But instead of t equals 2 and t equals 3, we'll do t equals 2 and t equals, how about 2.25? Okay. So we can compute this exactly the same way as before. So now this will be average velocity over a time interval that's sort of like more like what's happening near 2. So let's go back to the program. So now instead of f of 3 minus f of 2, we can do f of 2.25 minus f of 2 divided by 2.25 minus 2 on the bottom. So we get a different number. Now we get 0.5064. Okay. Let me come back and record that. All right. So I'm going to start making a list of these. Let me just copy this one. Copy this. Come to a new page, and we're going to start making a table. All right. So this is one entry, and so this is what we got over the interval from 2 to 3. This is the average velocity. And now we just did the average velocity over 2 to 2.25. And when we did that, we got 0.506431. Okay. It's a little bit worrying because these numbers are pretty different, right? So these, let's do it again. So now let's take an even shorter time interval from 2 to 2.0001. Sorry, in my calculations, it was actually this. So we'll do that. Let's go back to the calculator, change this number to 001, change this number to 001, and run it again. Okay, and now I get this number, and I'm going to go back to my other screen and add it to my table. So the number that came out is 0.4519711. Okay, and again, that number is different, which is a little bit scary. So we're trying to get closer and closer to the right answer. Hopefully, that's what's happening. Let's try this one more time. We're going to go from 2 to 2 plus 1 over a million. So this would be a very small change. It would be too small to see on the graphing calculator. I'm going to come back to this program and make that change. So this will be 6 zeros. I think it'll be 6 zeros. Let's make sure. So 2 plus 1 over a million. 2 plus 1 over a million. Okay, and get the answer. All right. Okay, so if you just look at this answer is actually not that different from what we had before. So this has turned out to be 0.4517668. And something kind of interesting has happened, which is the number has sort of settled down. So these 3 digits are actually exactly the same. And even these digits are not so far apart, right? 9 and 7 are pretty close. And then it kind of falls apart after that. So what you would see here, if you kept doing this, I don't know if we need to do it one more time or not. We could do 2 plus 1 over, I don't know, a billion. Let's actually do that. Let's change it to a billion. So what do we get then? All right, so I need to jot this down. 4517666729. Right, and I'll come back over to my other screen here. And the number that we just got is 0.451766729. And now let's see what's happening here in terms of our approximations. So this one agreed with the previous one all the way up to there. Wow. So we get agreement all the way up to there. And then 7 and 8 actually aren't so far apart. So do you see what's happening here? So we're defining a real number sort of a little bit at a time. And every time we make this time interval smaller, like now we could do like 1/10 to the 100 or something. So this would be a very small time increment. And what we would do then is we would determine some number up to like maybe, I don't know what it would be, like 30 decimal places or something. So 30 places. And then there would still be some noise out here in the end. This is like an infinite process that's never going to quite be complete. And the fact that this is an infinite process is kind of characteristic of calculus. In calculus, there's some precise number that you're talking about, but the number never arrives until you go all the way through some kind of infinite process like this. And it's called the limit. And that's why chapter 2 is a chapter on limits, because we're going to be, what we want to do is we want to take the limit as this quantity vanishes. So as this quantity vanishes, goes towards 0, what happens is this interval where you know the answer is going to expand until it's sort of infinitely long, and then that perfectly specifies just precisely one real number. And the meaning of that real number is the velocity of the ship at time 2. So you've already seen that I magically knew a function that describes those values. Let me just remind you what it is. It's this function right here. Let me zoom out a little bit. This purple function. So what the purple function is it's like the speedometer function. So if you pick some number here like 4, if you want to know how fast the boat is going at time 4, you just look up that value on the speedometer function. And so the answer will be the y value there. So at time t equals 4, the speed of the ship is like it's practically 2, right? It's about 2 feet per second. You can ask yourself, how fast does the ship ever go? The fastest the ship ever goes is about 2.5 feet per second, and that happens exactly at time t equals 5. So this is calculus 1 in a nutshell. You take some function, you can think of it as describing distance. We'll just think of it as distance initially. And then you somehow derive another function. This other function is like the speedometer function for the first function. It's called the derivative. And the way it works is if you plug in a certain time, and then you look up the value of the speedometer function at that time, the y value on that curve is the speed that the object was moving on in the first function. All right, so there's this whole story that we're moving toward how to compute the purple thing, and it's kind of a long story, but that's the road that we're on. We can come back to this. Let me turn this off, and let's come back to this geometric question. So we've seen sort of like numerically how that number is going to become more and more determined as this point moves over. So geometrically, we've seen that let me just put this picture back up here just to remind you. So this is also kind of characteristic of calculus. There's always like a story about the numbers, and there's also a corresponding story about pictures that tells you exactly the same thing. So in terms of pictures or geometry, what's happening here is you have this little change in time, delta t. You have this little change in location, delta s. And so the slope of the secant line for this point is going to be m equals delta s over delta t. And then you can ask yourself, what happens as delta t goes to 0? So as delta t goes to 0, here I can kind of do it with my slider. I turn off my drawer, I'll move this z down towards 0. Kind of hard to do. I'm trying to change z to be approximately 0. So notice that when z actually is 0, it blows up. So if I put z actually equal to 0, the problem with that is this would be f of 2 minus f of 2. What is f of 2 minus 2? 0, right? And then if the amount that I'm going over, delta t, if the amount that I go over is actually literally equal to 0, then what I get is 0 over 0, which is undefined. So it's kind of weird. So not only is the answer determined by this infinite process, but you have to do the infinite process. It's not like you can just plug in 0 into the formula. The world explodes when you plug in 0. If you come over here and do it in the program, if you just did this, what is f of 2 minus f of 2 divided by 2 minus 2? Then it's just going to say you're dividing by 0. So you can't do it that way. You have to sort of sneak up on the answer using this limit process. But anyway, so when we do that, let's come back to this picture. Let's jog this over just a little bit. There's a special line here. You might have heard of it before. Anybody ever heard of the tangent line? The tangent to a curve at a certain point is the line that just touches the curve at one point. This is a picture of it. Sorry, it's jumping all over the place. I'm going to push this off the top of my screen and I'll be in serious trouble. Let me actually stop sharing and then go back. Okay. Let me turn my thing back on. Oh no. Oh, this thing is stuck on. And this is a mess. Clear all my drawings. So the tangent line, the tangent to a curve at a point, let's call this a f of a. So I'm following the book here. The book just fixes this a certain a here. So we use 2, but in general this can be a. So this is a certain point here, a f of a. And there's a precise definition of the tangent, which I'm not going to give now because it involves limits. So is the slope of the line, and it's a literal line. That's why we're studying lines last time. The slope of the line that touches the curve y equals f of x. So in this picture that we have, y equals f of x is this red curve here. So it's the slope of the line that touches y equals f of x exactly at the point a f of a. And you can see me kind of sneaking up on that point by moving the slider. I come back to the mouse, pull this dot over. The secant line becomes more and more like the tangent line as that other point slides to the left there. And so right there, it's approximately right. So this is moving this slider over is the geometric version of what we were doing numerically by letting delta t become smaller and smaller. Let's turn this off. Let me just remind you here. We were numerically letting this delta t value get smaller and smaller. So in this stuff that we were doing here, this is delta t. So delta t was getting smaller and smaller and smaller. And as delta t shrinks, the average velocity becomes the instantaneous velocity. So this is the true instantaneous velocity. At time t equals 2. All right, okay. So that's it. It's kind of interesting that this number stabilizes at all, doesn't it? Isn't it? It doesn't always happen, but for like a broad class of functions, it does happen. And studying exactly which kinds of functions have this kind of stabilization feature is one of the things that we're going to talk about in the class, because you can make up some curves that that never happens for. Right. So now I'm gonna go to a different page. I seem to have hit some strange key. Go to this, and now let me just present all of this a little bit abstractly. So using certain notation, I'll draw some axes here. So here are some axes, and let's make. So now I'm just going to make some kind of curvy curve like this, and let's pick a point. So this will be A. This is the notation that the book uses. And then the book picks some other point over here, x. So you have a couple of things. You have this point on the curve, which is a f of a. This curve is supposed to be the graph of y equals f of x. Now we're moving away from the time picture, and this is just the x-axis, and this is just the y-axis. Okay. So this point is the point x comma f of x. Right? And you have the secant line that goes between those 2 points. Let me turn on my ruler. Okay, like this, right? So what this is the secant line for a, f of a, and x, f of x. And this is, how can you determine what that line is? So last time we talked about point slope form. So this line has a certain slope. The slope of this is f of x minus f of a divided by x minus a. And it also goes through a certain point. It goes through the point a comma f of a. So we could come up with an example where we sort of can actually literally figure this out. And how about we do that for a simple example right now. So let's say that y is equal to x squared. Let's say that a is equal to 1. And let's let x equal to, I don't know, 2 is simple. So then let's determine the secant line. Determine the equation for the secant line. So this will be easier if we can look at some kind of picture. So I'll try to draw some kind of picture. Here are some axes. You know, x squared is just a parabola. Here is a equals 1. And over here is x. And so x in this problem is going to be equal to 2. So tell me, what is the slope of the secant line going to be in this problem? Can somebody figure it out? There's the formula. Maybe I can get them both on the screen at the same time. Here's the formula for it. What I'm asking is, what is it in this particular case?
Is it going to be f of 2 minus, no, yeah, f of 2 minus f of 1 so, divided by 2 minus 1?
Yes, exactly right. So we can figure this out. So this is, the function is x squared. So this will be 2 squared minus 1 squared over 1. So that is 4 minus 1 over 1, which is 3 over 1, which is 3. The answer here is 3. Okay, so now we know the slope of the secant line. But we want to do a little bit more. We want to determine the equation for the secant line. So I tried to kind of get you ready for this last time because we talked about the point slope form of a line. When you know a point and then you also know the slope of the line, you can write down the equation using the point slope form. The formula is like this. y minus y1 equals m times x minus x1. This is the point slope form of a line. You can Google that if you want to. And so this x1, y1 in this formula is just going to be this point, which is 2, 4. Okay, so it's 2, 4. And we'll just fill in those details. Now we know everything about this expression. So this expression is really y minus 4 is equal to the slope, which is 3, times x minus x1, which is 2. Okay, so the formula is y equals 3 times x minus 2 plus 4. Sorry. Okay, and we could write this in more standard form like this. This would be y equals, I'm going to distribute this 3. So this becomes 3x minus 6 plus 4. So the final answer in standard form would be 3x minus 2. Okay, so that's the solution to this exercise. So let me stop lecturing now and go over to the homework, and we can look through and do some of your homework problems. Oops. Okay, so now we have several questions here that we want to do on this material. All right, so we'll just do a little bit of each of these problems maybe. So here we have the position of some of these are randomized and some of these are not. This problem I believe is not randomized, so I can't just tell you the answer because the answer would be the same for everyone. But I can work on it a little bit. So let's do this first part here. Whoa, that's too thick. So we have find the average velocity for the time period beginning when t is equal to 2 and lasting 3 seconds. So what is that going to be? That's going to be delta s over delta t. And delta s is going to be f of 2 plus 3 minus f of 2 divided by 3 minus 2. And we can look this up. These f values are going to come from this table right here. This table is saying that 2 plus 3 is 5, right? So the corresponding value is 11. So this will be, sorry, 111. 111 minus the value for 2 is 37. And then 3 minus 2 is just 1. So the answer to this problem is 111 minus 37. You might even be able to write it in just like that. Let's see if we can. What if I type in 111 minus 37? Check answers. So let's actually compute that. So 111 minus 37, 74. See if you like 74 better. Check answers. No. What am I doing wrong? Oh, it's because it lasts 3 seconds. I forgot about the, this was not right. Where I wrote 3 here, that's incorrect. Okay, so come back here. This should not be 3, it should be 5. Okay, so, and then instead of dividing by 1, we should be dividing by 3. Okay, sorry about that. And if we come back to this thing, we type in 74 divided by 3, then we get 24.66666. Let's come back here. See, we'll just do it this way. 74 divided by 3, and that's the correct answer. All right. So we could do the second one here, but all these questions are really similar, so I'm going to move on and just work on a different part of another problem. So if a ball is thrown straight up into the air with the initial velocity 80 feet per second, its height in feet after t seconds is given by this formula, 80t minus 16t squared. Find the average velocity for the time period beginning when t equals 1 and lasting, let's just do, instead of doing the first one this time, let's do this middle one. Let me get my pen. Okay, so I'm going to do this one. So now the interval that we're talking about is the interval from 1 to 1.01. We're going to take the average velocity over that time interval. And the average velocity, like it always is going to be the change in location divided by change in time. Okay, so the change in time in this problem, they just tell it to you right off the bat. It's 0.01. Okay, and we need the change in height. So that's going to be f of, I'm going to leave that blank for a second and then just write minus f of 1. Can somebody tell me what goes in the blank there? What should I write in that blank? What I should do is I should add the time difference to the initial start time. So this will be 1.01. Okay, so this is how I do this problem. And okay, so let's actually do it together. So I'm going to jot down on a piece of paper that particular formula is 80t minus 16t squared. And we're going to remember that the time interval that I care about is from 1 to 1.01. And you can do it differently if you prefer, but what I'm going to do is come back to the Sage Cell server. I still have to clear this stuff off my screen. It didn't go. Okay. And all right, so now I'm going to be working with a different function. The function that this question is asking about is 80 times t minus 16 times t squared. All right, and do this a little bit differently. So let's just call this the velocity. So we want 1.01, that's what we said before, minus f of 1. And then we could write 1.01 minus 1 there. Or we could just write the time difference, which is 0.01. And I'll evaluate here and get the answer. The answer is 47.839999. So I'm just going to call this 47.84 and come back to this sheet. Well, let's try 47.84. Check answers. Yes. Okay. All right. And now it says, what is the, based on the above results, guess what the instantaneous velocity of the ball is? If I was more confident that this was randomized, I would do that. That's such an interesting question. I want to let people figure that out for themselves. Still have time to ask about it next period if you want to. So this question is using slightly different notation, so let me explain that. Let's add some.
I have a question about the velocity. So it's basically just finding the slope, in like a graph.
That's right. Yeah. So there's always a graphical question, which is, in this case, is finding the slope of the secant line when you go over by 0.01, and then there's like a a functional way to understand it, which is this formula. You just give the formula in general. M is equal to f of a minus, sorry, I did it wrong. Where's my eraser? I need to get better at this. I will get better as the semester goes on. So this would be f of x minus f of a over x minus a. So this is sort of kind of always the answer. You can interpret that as the slope of the secant line, or just as sort of a function of x.
Yeah, so here's like, it's just interpreted as like the speed and the time and the distance, right?
Yeah, yeah.
Okay.
That's what everybody was thinking about when they first started working on this stuff back in like 1660. So let me try to draw a picture. So this is what natural log looks like. You might not have seen this function for a while. Here's y equals natural log of x. And so it says q is the point. Oh, so they give us a fixed point here. This is 2, should be like right here. Oh, that's so far from straight. I'm sorry. So that's 2. So here's the point, 2 comma natural log of 2. So this is going to be like a in this formula. And then we're going to go over to some x. Here's x. And here you get this kind of abstract point, x comma ln of x. All right. And so you can make this formula apply to this particular situation. It's going to be f of, I'm sorry, what is f actually? So this is the natural log function. So f of x is natural log of x. This is going to be minus natural log of 2 divided by x minus 2. This is kind of a function of x. And what you've got here is a bunch of different values of x. So you can answer this question just by plugging values of x into that formula. So that can be kind of painful. So what I'm going to do is I'm going to jot down that function of x, natural log of x minus natural log of 2 divided by x minus 2. And I'm going to come back over, I'm going to clear all this stuff, and come back over here. And it says I'm still drawing. Right, so I'm going to enter, it's just a different function here. So now what I want is, I can call it m of x. M of x is equal to natural log of x minus natural log of 2 divided by x minus 2. Okay, and now I can figure out particular values here. If I come back to the homework, let me just get one of these here. So let's look at this one, 1.9. So it's asking what happens when x is 1.9. I'll come back over here and I'll print m of 1.9. And if you do that, it'll give you literally the correct answer. So I don't know if you could actually type this into WebWork or not. You can give it a shot and see. And so what happens if you, this might not work, we'll try. What happens if you literally paste that in to WebWork? This might work. Yes, actually it does, okay. All right, but what I was gonna say, if that didn't work, is you can get a numerical approximation by doing dot in there. That'll just give you a decimal number. If you prefer, you can just use this decimal number too. The same thing. Okay. All right. And let me just make sure there's nothing weird. This is basically the same thing again. Same thing again. This one is a little bit different. I'm not sure that, let me let you think about this for next time. And so I think you can do all of these problems. So what I want to do now, we have about 10 minutes left. I'm going to try something that I've never tried before. Let's pick one of these problems to all do together. And you can just do, for now, let's do my version of this question. So let's do problem 7 together, if everybody can bring this up on their own machine. And I'm going to stop sharing, and I'm going to try something called breakout rooms, which I've never done. So assign 22 participants to, let's say, 5 rooms. Okay. I'm going to open all those rooms. And now you should have all been invited to join a breakout room. And so we're going to take, please join your breakout room, and we'll come back here in 5 minutes. And you guys tell me what the answer to that question is, right? We'll go back. In case you can't bring it up, that's what we're trying to figure out.